In this video, we're going to be discussing exact differential equations. And before us is a problem. 6x plus y, quantity dx, plus 8x plus 8y, quantity dy equals 0. Now, the astute of you might think this is a homogeneous differential equation, and you would be right. You can use the methods of homogeneous DE in order to solve this. But for this one, let's try another method, the exact differential equation. On the right side here is a tip, basically. How would you know m dx plus n dy equals 0? How would you know this is exact? Well, if the partial of m with respect to y plus partial of n with respect to x is equal to each other, then you can say that this is an exact DE. Now, let us recap what is a partial derivative. A partial derivative of a function is a x and y is a function. Well, the partial derivative is the derivative of a function focusing on only one of its variables, because f of x and y is a multivariable function. We will focus on x while treating y as a constant. Again, if we treat it as a constant, it's not actually a constant, it's a variable, but we treat it as a constant in here because we're only differentiating with respect to x. Ergo, we're trying to find the change with respect to x, not with respect to y. And the inverse is true. If we find the partial derivative with respect to y, we treat x as a constant. So that's the partial derivatives done. Okay? And a note here, m and n are actually partial derivatives themselves. M is some function f, the partial derivative of some function f with respect to x. That's why we have dx here. And n is partial f with respect to y. Let me just change this. Yeah, partial f with respect to y. That's why there's a dy here. So we will use this knowledge in order to help us in here in this equation. So let me introduce to you another notation here. If this is in partial m with respect to y, this can be also written as m y, like this, and n partial n with respect to x can be written as n x. This is alternative notation, so we will be using this. So this is m, this is n. We can tell because the x and dy here. Uh, it could be any letter, honestly, but generally we use m and n here. So m, this is m, and then we put y. Since this is dx, we need to find the partial with respect to y, as with here. So this would be equal to 6x plus y. What's the partial derivative with respect to y? 6x. There's nothing indicating y there. So it is just a constant. So 6x is a constant in with respect to y. So it would be 0. Plus, derivative of y with respect to y is 1, as we all know. So this is just 1. And x equals, well, the derivative of 8y with respect to x is 0, since y is a constant in the x world. And derivative of x with respect to x is just 1. So we my equals 1 and x equals 1. This means we have an exact situation in our hands, and we need to use we need to use the method of exactly in order to solve this. How do we do that exactly? Well, we know m is 6x plus y. But we know what m is? It's also f, some function f, x. The partial f with respect to x. Again, that's why there's the x in there. So, if we integrate f with respect to x, we also need to integrate the other side. And from here, we can get the derivative of f with respect to x. The integral of that's just f. And in here, the integral of 6x is 3x squared. The integral of y is just a constant, so we can put that as constant. And then we have to multiply with the integral of that, which is x. All right. And then we need to add an arbitrary function. Why do we have to, why do I have to add an arbitrary function? Well, because this is just dx, and this is a multivariable question. So if we didn't have this arbitrary function, it's just plus c, it would be incomplete. Because any function that's just y is going to be zero when partial differentiated with respect to x. So we need to add a g of y here. And how can we find g of y? Well, let's just go back to the partial f with respect to y this time. 3x squared is 0. Derivative of that with respect to y is 0. The derivative of xy with respect to y is just x, since derivative of y is just 1, plus g prime of y. Now, fy is also n. And what is n again? Let's see. 8x plus 8y. We need to match this up one by one. So x becomes x and 8y becomes g prime of y. So g prime of y should be 8y. And to find the interderivative, we just have to integrate both sides. We get g of y, which is what we need, equals the integral of this with respect to y, which is 4y squared. We can put plus c here, but you will see where we put plus c. So let's write this. Let's forget the f for now, and let's write the entire equation. 3x squared plus xy plus g of y, which is now 4y squared. We can put plus c here, but let's put it on the other side, like that. And that's going to be the answer. All right, now let's proceed to the next problem. 2x plus cosine y quantity dx plus quantity x squared plus tangent y x squared tangent y plus cosine squared y is quantity dy equals 0. Now, this looks like an exact thing, and this is not homogeneous. So let's see if it's exact. Hold on. My is negative sine y, and then nx equals, well, 2x tangent y. This is not exact. So do we give up? Do we find another one? Well, maybe not. Maybe we can still solve this using a formula. What would that formula be? Well, let's say m dx plus n dy is a differential equation, and my is not equal to nx. This makes it inexact. This is not an exact differential equation. So how do we reconcile it? How can we make this exact? Well, can we multiply both m and n such that they would be exact again? Let's multiply it using the special integrating factor mu. This is not the linear mu, but this is a different case. This is actually the general case of the special integrating factor that we discussed in linear differential equations. So we need a formula that would make this exact, like that would make this situation equal each other. So this would be exact, right? So let's try solving this. First of all, let's establish some what do you call this? Whatever. Let's establish that mu is a function of x. Let's just put some brackets in here so we can differentiate. Uh, we can also assume y, but we will deduce that later that the formula would be very similar to what we have. So in order for this to be exact, this needs to be partial differentiated with respect to y and this with respect to x. And they should be equal in order for it to be exact. So how do we make this exact if my and nx is inexact? Well, let's uh let's do the process of partial differentiating both sides. So since mu of x is just a constant with respect to y, mu of x remains unchanged on the left hand side, and the partial derivative of m with respect to y is just my. On the other side, n and mu are both related with x, so we need to use the product rule. So n x, then mu remains unchanged, plus n remains unchanged multiplied by mu prime of x, the derivative of mu of x. Sorry. So now we have this. How do we isolate mu of x now? Let's transpose this term to the other side. So we get my mu of x minus nx mu of x equals n times mu prime of x. In here we can factorize mu of x out. So we get mu of x equals sorry, mu of x times my minus nx equals n mu prime of x. Let's put all everything related to mu on one side. So in the right hand side we get y mu prime over x over mu of x. On the left hand side we get uh, this over n. All right. With here we can spot how we can solve this, right? Integrate both sides with respect to x, the x. All right. This is an easy ln of mu of x. This is, well, we don't know what it is yet, so integral of my minus nx over n dx. Then we raise e to both sides. Canceling this, we get mu of x equals e to the power of my minus nx over n dx. If you want to memorize this formula, I have one thing that I remember is that nx is close to dx. So if you're doing this, my minus nx over n dx. Now, if that doesn't work or you can't integrate that because it's too hard, there's an alternative special integrating factor, which is of y. If you check, this is reverse of this, nx minus my this time over m dy. One thing you can remember is that the partial derivative with respect to x is always close to dx, and partial y derivative y is close to dy here. So there you go. These are the two formulas we can check. So let's go back to our question. Now, for this one, let's try both, right? So mu of x and mu of y. Mu of x is e raised to, first of all, since this is dx, so my, negative sine y, and then minus nx minus 2x tangent y over, uh, since this is n, we should divide by n, so x squared tangent y plus cosine squared y. And do you know a solution here? If you do, you can do that, but I don't know the solution for this one, and it looks like it might be very difficult. So we're going to backpedal a little bit, and use the mu of y instead. See if that works. If it doesn't work, you have to use something else. So just a little bit of warning. So nx 2x tan y minus negative sine y, so plus sine y over, on the bottom we get 2x plus cosine y. Is this still solvable? Tangent y really hurts. Can we get rid of it by dividing both the numerator and the denominator by tangent y? Let's try it out. So integral, let's just ignore the e for now. So 2x tangent y plus sine y over, oh, forgot that parentheses, 2x plus cosine y dy. What if we divided both sides by 1 over tangent y, sorry, 1 over tangent y. What happens in the upper one? Well, the tangent y is cancelled, leaving us 2x plus sine y times tangent y. Tangent is cosine y over sine y. Sines will cancel out, leaving us with cosine y over. Let's not touch 2x plus cosine y here. And this one tangent y is on the bottom, so we will put it on top like this. And what can we see? Doesn't that cancel each other out? So we're left with e to the integral of tangent y dy, which famously is e to the ln secant y. We can ignore plus c for now. E to the ln cancel each other out. We get secant y. Again, we can still ignore c, you know, like the linear differential equation. So our special integrating factor mu of y is secant of y. Now, let's multiply it back to the original differential equation. We will get, hold on, 2x secant y plus 1, since cosine y times secant y is just 1, quantity, then dx, plus x squared secant y tangent y plus cosine y, and then dy equals 0. Now, from here, we are guaranteed, if we did all the steps correctly, that this is an exact DE. So do we need to check? You can, but I'm not going to check anymore since I already know that this is exact. But you can still check. So this is M, well, M new. So let's call it M. Let's just call it M. Let's just call it new M, just M, right? So M new, and then M new is equal to F new. I don't know. Let's just say it's M. Another M. So this is M. We know M is F with respect to x, which is equal to 2x secant y plus 1. So the integral of both sides. The integral of it with respect to x is just F. The integral of this is uh since secant y is just a constant in the x world, we can say it's x squared secant y. And then plus 1 invites plus x here. And then g of y here as the arbitrary function with respect of y. So the derivative with respect to y now, which is equal to n, should be, well, the derivative of y here is secant y tangent y. So x squared secant y tangent y. And then x is just a constant in the y world, so that would be 0, plus g prime of y. Now, we know that n is equal to x squared secant y tangent y plus cosine of y. So we know that g prime of y is cosine of y, and g of y now, the integral on both sides is sine y. We can put plus here. So now that we have found g of y, we can insert it back into the f, but let's ignore the f now. So x squared secant y plus x plus sine y, then we can equate c on the other side, and this is your general solution. I hope you learned some exact and inexact equations, and I'll see you in the next one.